Welcome back to the deep dive. It's pretty late here. The coffee is brewing, and honestly, this is just the perfect time for the conversation we're about to have.
Oh, yeah. The late night vibe is definitely required for this one.
Right. So if you're an engineer or even just a tech-curious person watching this massive AI explosion from the sidelines, you already know the score. You know machine learning isn't magic.
It is definitely not magic. I mean, no matter how magical the output feels when you're chatting with a bot, underneath it all, it's really just statistics at an absurd scale.
Exactly. There's no wizard behind the curtain. There's code, there's math, and a whole lot of hardware.
I said.
But the terminology is an absolute swamp.
Oh, completely.
You constantly hear things like training, fine-tuning, rewards, unsupervised, self-supervised, and it all just starts to blend into this white noise of buzzwords. So our mission for this deep dive is to cut right through that noise.
Yeah, we're going to peel back the layers of how machines actually learn.
Right, getting into the specific mechanisms that power everything from your basic email spam filter all the way up to GPT-4.
And what I love about this topic is that it's not just about the code. It's really about the philosophy of learning itself. The structures we've built for machines mirror the different ways we learn as human beings.
Which is exactly where I want to start, because the research we're looking at today uses this fantastic framework to set the stage. It breaks it down into two main ways humans learn. So method A is what I like to call classroom mode.
Right, the traditional way.
Yeah, you're sitting at a desk, you have a teacher right next to you, they point at a flashcard and say, that's a cat. They point at another and say, that's a dog. It's very explicit, directed instruction.
And in data terms, you are getting the answer key handed to you right along with the test materials. You're never really guessing without getting immediate feedback.
Precisely. But then you have method B. And this is like walking into a party where you don't know a single person. Or, better yet, being dropped into a foreign country where you don't speak a word of the language.
Oh man, yeah. That is a completely different cognitive process.
Completely different. No one is explaining the rules to you. No one is telling you who's important, what the social dynamics are, or what the words mean. You just have to figure it all out purely by observation.
You're looking for patterns without a guide, trying to synthesize structure out of pure chaos.
Right. And the thesis for today is that these two distinct human experiences map almost perfectly to the two classic pillars of machine learning, supervised and unsupervised learning.
But, and here's the hook for today, neither of those fully explains the AI revolution we're living through right now.
They really don't.
They are the foundation, absolutely. But there's a secret third mode, and actually a fourth one too, that changed the game entirely. That third mode is the reason we have large language models today. It's the bridge between smart code and actual AI.
We're definitely going to get to that secret sauce because it's the climax of this whole story. But let's unpack those basics first so we can see why that shift was so massive. Let's start with the teacher. Supervised learning.
Yeah, so supervised learning is usually the most intuitive one for people to grasp, especially if you come from a programming background. The name really says it all. There is supervision.
Right.
In data terms, this means you have a data set where every single input comes with a corresponding ground truth label.
Ground truth, that's a really key term here.
It is. It's the absolute verified correct answer. So if you're training a self-driving car, the camera image is your input, and the label, which is provided by a human, is stop sign or pedestrian.
The sources use this analogy of a post office, which I found really useful to visualize the actual mechanism. Imagine you're training a new employee to sort the mail.
Okay.
You don't just dump a massive pile of letters on their desk and walk away. You sit next to them, you pick up a letter and say, okay, see this? This goes to Dublin.
Okay.
You pick up the next one, this one, Cork, then Galway.
And that is the absolute essence of it. The machine, or the new employee in your analogy, is looking at the input, which is the letter, and predicting the output, which is the sorting bin.
Right. And at first, the machine is essentially just guessing.
Exactly. It has random weights. But because you are there to correct it immediately, it calculates the error. In math terms, we call this the loss function.
The loss function.
Right. It realizes, oh, I guessed Cork, but it was actually Dublin. I need to adjust my internal parameter so I don't make that exact mistake next time.
So it's this constant loop of guess, check against the ground truth, and adjust. And over time, they start to recognize the patterns on their own. They see the postcodes, they recognize handwriting styles.
Yeah, and eventually they can sort mail they have never seen before because they've internalized the rules from those explicit examples.
Which is incredibly powerful. And within this supervised world, the research highlights two main flavors, classification and regression.
Right. Classification is exactly what we just described with the post
Yeah.
office. You're putting things into buckets. Is this email spam or not spam? Is this MRI scan a malignant tumor or is it benign?
You're drawing boundary.
Exactly. I like the visual of the decision boundary. If you have a graph with red dots and blue dots, the computer is trying to draw a line or maybe a curve that separates them perfectly. In complex AI, that line becomes a multidimensional hyperplane, but the core concept is exactly the same: separation.
And the other flavor is regression. This is where you aren't picking a bucket or a category, you're predicting a continuous number, like trying to predict house prices.
The classic textbook example: you have the square footage, the neighborhood, the number of bedrooms. Those are your inputs, your features.
Right.
The output isn't a category like expensive or cheap, it's a specific dollar amount. You are drawing a line through the trend of the data, fitting the curve, to predict a numerical value.
Okay, so supervised learning sounds great. It's accurate, it's highly controlled, but there is a catch. And looking at the industry right now, it seems to be a pretty brutal, expensive catch.
Oh, it's a massive bottleneck. The catch is the labels themselves. Remember, for supervised learning to work, a human usually has to provide that ground truth. If you are building a medical AI to spot cancer, you can't just have random interns guessing. You need board-certified radiologists to look at thousands of scans and physically circle the tumors.
That sounds incredibly slow and wildly expensive. I can't imagine top-tier radiologists are cheap to hire for what is essentially data entry.
They are definitely not. There are entire massive companies like Scale AI that were built just to solve this specific problem by hiring armies of human labelers for everything from self-driving cars to legal document analysis.
Wow.
And there is a huge risk here too: garbage in, garbage out. If your human labelers make mistakes, or if the labels are inherently biased, your model hits a performance ceiling it can never break through. You just can't learn truth from bad data.
That makes total sense. So if supervised learning is the expensive, high-effort teacher, let's flip the script. Let's talk about the foreign country mode, unsupervised learning.
This is where things get really interesting mathematically.
Right.
In unsupervised learning, you have the data, maybe millions of documents or images, but you have zero labels.
No answer key.
No answer key, no teacher. The machine has to find the structure completely on its own.
So going back to that foreign country analogy, you're dropped in, you don't speak the language, but if you sit on a park bench long enough, you start to realize, okay, everyone rushing that way is wearing a suit. It must be rush hour.
Right.
Or people bow when they meet. That must be a formal greeting. You are finding the patterns just by existing in the data stream.
Precisely. You are inferring rules from the distribution of the data. And in machine learning, one of the main ways we do this is a technique called clustering.
Like sorting laundry without instructions.
That is a perfect way to put it. Imagine a huge pile of clothes. Even if you don't know the English words for socks or shirts, you can see that these small woolly things look similar to each other, and these large denim things look similar to each other.
So you just group them based on inherent similarity.
Exactly. Algorithms like k-means do exactly this. They look for data points that are close to each other in the mathematical space.
What is the killer use case for this in the real world? Because I have to imagine businesses absolutely love the idea of not paying human labelers.
Oh, customer segmentation is huge here. You feed an algorithm millions of purchase histories. You don't tell it what to look for at all, but it comes back and says, hey, I found a distinct group of people who only buy luxury items on Tuesdays, or here is a group that buys baby diapers and beer on Friday nights.
Wait, diapers and beer, is that an actual correlation?
It's a classic data mining anecdote, yeah. The algorithm finds a correlation between exhausted new parents buying supplies for the weekend, diapers for the baby, beer for themselves.
That is amazing.
You didn't predefine those groups. The math just found the hidden structure for you.
Wild. Now, there's another technique mentioned in the sources here called dimensionality reduction. This sounds a bit more sci-fi to me, but the notes say it's absolutely critical for handling big data.
It sounds complex, but it's really solving a very practical problem, which we call the curse of dimensionality. Imagine a data set where every single data point has 10,000 features.
10,000.
Yeah, maybe it's a deep genetic profile or super high-res image. Humans cannot visualize 10,000 dimensions. We can barely handle 3.
Right, so we need to squash it down somehow.
Exactly. The best analogy here is making a map. The Earth is a 3D sphere. To put it on a flat piece of paper, you have to squash it into 2D. You lose some info, like Greenland might look way too big on a Mercator projection, but you gain a usable big picture view.
Okay, I see.
Techniques like PCA principal component analysis or TSNE take that 10,000 dimensional data and basically project it onto a 2D or 3D map so we can actually see the clusters.
So it effectively simplifies the noise so we can actually see the signal.
Exactly.
Okay, so we have supervised high effort, high accuracy,
Yeah.
and we have unsupervised low effort, finding hidden structures.
Mhm.
But the sources also mention a bridge between them, a hybrid model.
Semi-supervised learning. And honestly, this is where most real-world industry problems live today. Because usually you have a mountain of raw data, but you only have the budget to label a tiny fraction of it. So it's like you have a million photos, but you can only pay someone to manually label 1,000 of them.
Right, so you use that small labeled set to find anchors. It's like having a tour guide show you just the financial district and the arts district of a new city.
Okay.
Once you know those two specific vibes or feature sets, you can walk around the rest of the city and figure out, okay, this street has a ton of galleries, so it's probably part of the arts district, even though the guide didn't explicitly tell you that.
You propagate the labels from the known to the unknown.
Exactly.
But does that actually work well?
Hmm.
Or does it just dilute the overall quality of the model?
The stats on it are surprisingly impressive. The sources note that sometimes labeling just 1% of the data can get you 90% of the performance of a fully supervised model.
Wow.
Yeah, it is a massive efficiency hack.
It sounds like the perfect sweet spot. But, and here is the really big, but even semi-supervised learning wasn't enough to get us to ChatGPT. It wasn't enough to understand language on a deeply human level.
No, it wasn't, because language is just too complex to simply cluster. You can't just group sentences into happy and sad buckets and expect the machine to write a coherent poem. Which brings us to the main event.
The secret third mode, self-supervised learning. The notes call this the engine behind modern LLMs. What makes this so different from just unsupervised learning?
The distinction is subtle but completely revolutionary. In unsupervised learning, you're just looking for clusters. In self-supervised learning, you are actually forcing the machine to play a game with itself to learn deep relationships. The absolute key idea here is the data is the label.
The data is the label. Okay, that sounds a bit cryptic. Let's unpack that.
Think about how GPT models are trained. You take a normal sentence from the internet, the cat sat on the format, and you hide the last word. Then you ask the model, what comes next?
And it guesses Matt.
Right. And then you reveal the actual word. If it was Matt, the model gets a thumbs up. If it guessed toaster, it gets a correction, a gradient update to its internal weights. But here is the magic.
You didn't need a human to label that.
Exactly. The sentence itself contained the answer.
I see. So you can literally take the entire internet, trillions and trillions of words, and turn it into a massive training exercise without hiring a single human labeler. The text itself provides the supervision.
Exactly. This is called autoregressive training. And there's a famous quote from Ilya Sutskever, one of the co-founders of OpenAI, that really explains why this works so well. He said, prediction is compression, and compression is understanding.
That is a deeply philosophical thought, but I'll play devil's advocate here. Isn't it just fancy autocomplete? Why does predicting the next word actually lead to intelligence?
That is the most common criticism. But think about what is actually required to predict correctly in a highly complex scenario. Imagine you're reading a dense mystery novel. You are on the very last page. The detective gathers everyone in the drawing room and says, the killer is.
Well, to predict the name, you have to have understood the whole book.
Exactly. To predict that one single word, you need to remember the motive from Chapter 3, the fake alibi from Chapter 6, and all the subtle relationship dynamics established throughout the story.
You need logic, reasoning, and context.
Yes, by forcing the model to predict the next word over billions and billions of examples, it is essentially forced to internalize logic, sentiment, and hard facts about the world. It's not just memorizing text, it's modeling the underlying reality that generated the text in the first place.
So to play the game well, it literally has to become smart.
Precisely. And there's another flavor of this called masked language modeling, which is what Bert used. Instead of predicting the next word at the end, you take a sentence and black out a word right in the middle, like a closed test from grade school.
The blank sat on the mat.
Right. The huge advantage there is the model gets to look at the context from the words before and after the blank simultaneously. This gave us incredibly robust bidirectional language understanding. And the crazy thing is, this technique isn't limited to text. We see contrastive learning in images too.
How does that work? You can't really predict the next pixel quite the same way you predict a word, right?
No, predicting raw pixels is incredibly messy. Instead, you take an image, say a photo of a dog. You make a copy of it and distort it. Maybe you turn it black and white or crop it tightly or rotate it.
Okay.
Then you show the model the original and the distorted version and say, hey, these two different looking images are actually the same fundamental thing. Then you show it a picture of a cat and say, this is different.
So the model has to learn to recognize the core identity of the object.
Yes, the concept of dog, despite all the visual distortion, and again, absolutely no human labels needed.
This really feels like the unlock code for AI scaling. You stop relying on slow humans to teach, and you just let the vast ocean of data teach.
That is exactly why we saw the sudden explosion in capability. We completely broke the dependency on human labor for the heavy lifting of the learning process. But, and this is crucial, we aren't done yet. Because if you just have a model that predicts the next word, it might not actually be very helpful to a user.
Right, because if you ask it, how do I make a bomb? It might just enthusiastically predict the next words from an anarchist chemistry textbook. Doesn't know it shouldn't tell you. It's just completing the pattern it saw online.
Exactly. It has no intrinsic moral compass or goal other than pattern completion. And that brings us to the final paradigm we need to cover: reinforcement learning. Which feels very different because it's not about finding patterns in a static data set, right?
Completely different. This is about an agent operating in an environment.
Think of it like training a dog. You don't show a dog a spreadsheet of good behaviors.
Trust me, I have tried. They do not read Excel very well.
No, they really don't. You use rewards and punishments. You give them a treat when they sit. You say no when they chew your shoes. That is the core of reinforcement learning. The AI tries an action, gets a reward, basically a generic +1 or a penalty, and it adjusts its strategy to maximize those rewards over time.
This is how DeepMind's AlphaGo beat the human world champion, right? It played millions of games against itself, learning which moves led to a win. The win itself was the reward.
Exactly right. But the really fascinating part for our listener today is how this exact concept plugs into a system like ChatGPT. It's a specific process called RLHF, reinforcement learning from human feedback.
Okay, so how do we actually combine the dog training approach with the massive autoregressive text predictor?
So you take that self-supervised model, the one that read the entire internet. It's incredibly smart, but it's chaotic. Then you have it generate a few different answers to a prompt. Human testers look at two answers and say, this one is better.
And that human preference becomes the treat.
Yes. You train a separate, smaller model to learn what humans generally prefer, and then you use that model to automatically give treats to the main AI. The model learns to shave its vast, chaotic knowledge into answers that humans actually find helpful, polite, and safe.
So it's a stack. It's basically a layer cake of different learning methods.
A perfect layer cake. If you look at the modern AI stack for something like ChatGPT, it uses all of these in sequence.
Right.
Layer 1 is self-supervised. It reads the raw internet to learn how language and the physical world work. This is the heavy lifting phase. Then layer 2 is supervised. You fine-tune it on some high-quality instruction data to teach it the specific format of Q&A.
And then layer 3 is the reinforcement learning. You align it with human values using RLHF so it doesn't just go completely off the rails. That makes so much sense when you break it down like that. It really is an orchestra of all these distinct methods. And the notes actually have a great practical example of how this might look in a robust spam filter, not just a basic keyword filter, but a modern, really good one.
Right, let's walk through that because it makes it super concrete for the listener. First, you might use unsupervised learning to just cluster all the incoming emails. It notices, hey, these thousands of emails all have similar weird links, and these emails all talk about family events.
It doesn't even know which is spam yet, just that they are different distinct groups.
Exactly. Then you use semi-supervised learning. You have a human label, just a few of those clusters. Maybe you mark one weird link email as spam, and the system automatically propagates that spam label to the rest of the millions of emails in that cluster.
Then comes the heavy lifter, the self-supervised pre-training. The model has already read billions of normal emails, so it deeply understands the nuances of language. It knows that urgent business proposition is likely sketchy based on the context of the words, not just because it hit a static keyword list. It understands the underlying tone.
Spot on. And finally, you bring in reinforcement learning. Every single time you, the listener, hit the mark as spam or not spam button in your inbox, you are giving the system a reward or a penalty. You are actively teaching it to be better for you specifically.
It adapts directly to your behavior.
Exactly.
It is genuinely amazing how these things that we usually treat as separate, isolated textbook chapters are actually just interwoven components of one big, elegant system.
And if you look at the overarching trend line of the last decade in tech, there is a very clear direction. We're rapidly moving away from methods that require high human effort.
Right, because supervised learning requires maximum effort. You need a human label for absolutely everything.
Yep. Then semi-supervised requires moderate effort, but self-supervised and unsupervised require almost zero human labeling effort.
And as we move down that list towards less human effort, the scale of the raw data we can process goes up effectively to infinity.
That is the fundamental trade-off that defined the last decade of AI development. We figured out how to trade human precision for massive, unbelievable scale, and scale one.
Scale one. That is a really powerful summary. We started this deep dive with a teacher pointing at a flashcard of a cat, and we ended up with a machine teaching itself by reading the entire internet and playing endless games against itself.
It is a remarkable evolution. And really, we only talked about the types of learning today. We haven't even touched on the physical architecture, the actual neural networks themselves.
Which is the perfect teaser for our next deep dive. Because knowing how it learns is one thing, but understanding the actual history of the neural net and the infamous AI winters, where everyone in the industry thought this tech was a total dead end, that is a massive story all on its own.
Oh, the history of deep learning is filled with academic drama. It's definitely worth a dive.
We will leave that for next time. For now, hopefully the next time you hear a buzzword like self-supervised learning, you won't tune out. You'll know it's the secret sauce that makes your chatbot sound so incredibly smart. Thanks for listening to The Deep Dive.
Keep learning.
See you next time.